figured I would whip together a quick, sorry if my head's cut off. I just figured I would whip together a quick video just going over quotient spaces for those who couldn't make it. Obviously this is an enrichment, so it's not necessary for you to know by any sense, but I didn't record, and I think there were a few people who missed the all or some parts of the little lecturette, so I just wanted to go over it just in case you're interested. So we started by talking about the idea of equivalence. In and of itself. So we said that two vectors, so we start off by saying, well, let's let V be a vector space, and let's let W be a subspace of V. And then we said our definition was that U and V in W, so U and V in V are equivalent if and only if U minus V is a vector in W. So it's that not necessarily that U and V themselves are in that subset W, but that when you subtract them from each other, you get a vector that's in W. If that's true, then we say that they're equivalent under W. And we write U is equivalent under W to V. Or, more simply, if W is sort of assumed, we can just write U is equivalent to V. You can drop the W if there's not multiple subspaces going on. So as an example, I gave the example 0, 1. We know that that is equivalent to 1, 1. Specifically, if we look at V to be R2, and we look at W to be the span of 1, 0. Because if I do 0, 1 minus 1, 1, I get 1, 0. So I get something that's inside W, some element of W. Another example might be under the same two vector spaces, maybe like 3, 5 is similar to 7, 5. So you'll notice they kind of make these groups of things that are all equivalent to each other. These sets of things that are all equivalent to each other. And that's important. That's called an equivalence class. So we say an equivalence class, we put square brackets around the vector, which some people get confused because if you actually write out what the vector is, now it looks like there's a double square bracket around it, but it's really just square brackets around a vector. And so an equivalence class is a collection of elements that are all equivalent, of vectors that are all equivalent. So definition is that this is equal to the set of V plus any combination of things that are in W. So if, we'll maybe write this out. If B1, B2 through Bn are a basis for W, capital W, then the equivalence class of V is equal to the set that contains elements that are V plus some number times B1 plus some number times B2 plus some number times Bn for some arbitrary constants alpha 1 through alpha n. So hopefully that makes sense. Another way you could think of it, for example, is it's just a collection of all the things that are equivalent to each other. So as an example, the equivalence class that contains 0, 1 is going to contain 0, 1 itself, it's going to contain 1, 1. It'll contain 2, 1. It'll contain -7 and 1. It'll contain a bunch of things. Now notice, in this example, it really comes down to that second element, but that's just because of the specific choice of subspace that we did. You could choose different subspaces. It could have, this subspace only has a basis or dimension of 1. You could have subspaces that have multiple dimensions, so it could sort of get more complicated, but this is just sort of our toy example. I'm going to erase this, and we'll sort of go on from there. The first problem that the group did was to show that equivalence, as we defined it, is a equivalence relation. And you might remember equivalence relation, which is completely unrelated to what we just described. So I'll write out the definition of an equivalence relation. This is something that you possibly did in discrete math, in whichever version you took. An equivalence relation is a relation, remember where we did like A is related to B, that sort of thing. It's a relation that satisfies 3 criteria. First, it must be reflexive. So what that means is that A is related to A. Second, it must be symmetric. So what that means is that if A is related to B, then B is related to A. So order of relation doesn't matter. And third is that it is transitive. So that's if A is related to B, and if B is related to C, then A is related to C. So those 3 things are true, then you have what we call an equivalence relation. Okay, so the problem was to show, so problem 1 is to show that equivalence under some subspace forms an equivalence relation. An equivalence relation. So it must meet those axioms. All right. First, we have to show that this is reflexive. In other words, we need to show that any vector is related to itself. So we want to show that U is related to U. So what we'll do is we'll do U minus U. We want to show that that's in W. Well, U minus U is the 0 vector in the larger vector space V. And I should note here that we're assuming V is a vector space and that W is a subspace of V. And we want to show this, of course, for all U in V. So U minus U is the 0 vector in V, but the 0 vector in V is also the 0 vector in W, since they're subspace, or W is a subspace of V. Since it's the 0 vector in W, that means it's in W, so therefore U is related to itself. For 2, we want to show that if A is related to B, so we're going to suppose that U and V are in V, and we'll suppose that U is related to V. What that means, we won't end up showing that V is related to U, that we can swap them. So that means that U minus V is in W, but then V minus U is equal to negative U minus V. And negatives of vectors, that's one of the axioms, is that every element has a negative in the vector space. So since this is in, this piece here is in W, that means the whole thing has to be in W. So that means that V is related to U. And third part, transitivity. We'll start by supposing that well, let's use some better number or systems here. So we'll do V1 is related to V2, and we'll assume that V2 is related to V3 for V1, V2, V3 are vectors in V. So what that tells us is that V1 minus V2 is a vector in W, and v2 minus v3 is a vector in W. I'm going to add those two equations together. I'll get v1 minus v2 plus v2 minus v3. And since we're adding two vectors in W, we know by closure that this has to be a vector in W. These cancel each other out, and we're just left with v1 minus v3 is in W, which tells me that v1 is related to v3. So that's sort of the core here. Hopefully that makes a little bit of sense. If it doesn't, give it a try on your own and see if you can derive the same conclusions. I'm going to erase, and now we'll go on to talking about quotient spaces, which is the main sort of part of this that we were working up to here. All right, so the first thing we have to do, so to talk about quotient spaces, we need to talk about something called cosets, which we've sort of already talked about. This is another framing of equivalence relations. Cosets are when we take that equivalence, sorry, not relation, equivalence class. Cosets are when we take those equivalence classes and we sort of treat them as objects themselves and start to do operations on them. So, start by thinking about the equivalence class 0, 1. Again, we're going to use the same, and W is the span of 1, 0. So we'll think about the equivalence class containing 0, 1, set of all things that are equivalent to 0, 1 under W. And I should also note sometimes they'll put a little W on the outside just to indicate that this is equivalence classes under W. Same thing with how we did the equivalence symbol with a little W. Same sort of idea. If we have two cosets, so you'll notice that these two cosets, or these two equivalence classes, are different. 0, 1 and 0, 2. They contain different things. I'll let you think about that and show it. If I add those two equivalence classes together, we're defining this addition to work in a standard way with equivalence classes, and that's sort of what the coset piece is. So this will give us 0, 3. So in general, what we're defining is we're saying the equivalence class of V plus the equivalence class of W is the equivalence class of V plus W. That's how we're defining addition. For scalar multiplication, we're doing something very similar. If I do 2 times the equivalence class generated by 0, 1, I'm going to get the equivalence class generated by 0, 2. And in general, K times the equivalence class generated by U is the equivalence class generated by KU. So this whole setup here, this leads us to the idea of a vector space, right? We're seeing a definition of addition, a definition of scalar multiplication. A natural question might be, does this weird system meet all of those axioms of a vector space? It turns out that they do for any arbitrary W. So it doesn't have to specifically be this one, but in general, they do. And the vector space that we're talking about here is what we call the quotient space. So at the start of, and I think I might have missed this in this recording, but at the start of our tutorial, we said, what are different operations we could do on sets? We said, well, if we have two sets A and B, we might think of the Cartesian product between them, multiplication. We might think of the direct sum of them. We might think of the difference, the set difference, where we do everything in A, drop everything in B. Natural question might be, can we divide sets? And that's exactly what we're doing here. We're creating these equivalence classes, which is the division of sets. All right, it classifies them into groups. So you can think of it that way. We're classifying all of A into groups based on B. And that's the logic. So the way we ended class was by saying, can we prove that W, V quotient with W is a vector space for arbitrary V and W. And if you can't quite do that, start with R2 divided by the span of 1, 0, which is the example we've been working with all along. And yeah, you can play around with other examples, right? Pick arbitrary an arbitrary vector space and a subspace in there, and see if you can, play around with it and see what you get. That's the logic with quotient spaces. Hopefully that's helpful. Yeah. If there's any questions, you can feel free to let me know, send me a message, or drop by my office, drop by study hall. I'm more than happy to help. And yeah, hopefully that's helpful.